So, welcome everybody. It's my special pleasure to have Peter Topping here, who will talk about the uniqueness of limits in geometric flows. Please.
Okay, thanks very much for the invitation to speak in this nice seminar. I'm going to try giving an iPad talk. Let's see how it goes. So I'm going to be talking about joint work with James Kohout and M.Rupflin. They're both at Oxford. And it's going to be mainly to do with a gradient flow for a harmonic map energy. But I want to give you a sort of overview of the sort of general problem of uniqueness of limits. Okay, so as I said in the abstract, so limits in geometric flows can often be extracted with soft compactness arguments. So what do I actually mean by that? So I thought I'd start off by giving you a very simple example where that happens, but already something interesting can occur. So what I'm going to consider is, just start off by considering a map U0 from S1 to N. So what is N? So this is some compact Riemannian manifold. And for simplicity of the PDE, let's embed that isometrically in some Euclidean space. Okay, so what I want to do is evolve it under the harmonic map flow. So what actually is that? So that's a gradient flow, the L2 gradient flow for the harmonic map energy, which I've written here. So actually I've written it in a sort of general form which would work for a map from any manifold to any other manifold. But of course, I'm starting off here working from S1. So really what this du squared is just u sub s squared. And this is really just ds. Okay, so this is actually giving a nice PDE. So let's see what that is. So the PDE for u is du by dt equals something called the tension field. I normally write it tau of u. And the easiest way of writing that, the briefest way of writing that, is to take the Laplacian of u. So u I'm thinking of mapping into RK, remember? And so I take the Laplacian of u, but then if I did that, then I'd end up with a vector which was not tangent to the target manifold n. So I need to project, so I normally write that with a little t there. Okay, so that's the starting PD, which will be useful later as well. Okay, so this is a subcritical PD. Everything is very nice. You get long time existence and all the bounds you want. So everything is particularly simple in this situation. So what we can do is we can pick a sequence ti goes to infinity. Normally you have to be a little bit careful about the sequence, but here you can do pretty much what you want. So because of the nice estimates you get, you have a uniform bound for, let's say, the CK norm, any k, and the tension is going to go to 0. So just the most straightforward form of compactness will tell you that you can pass to a subsequence and get a convergence to a limit. Okay, so that convergence in this situation will be smooth. So that limit's going to be a harmonic map from S1 to N. So that's actually going to be a geodesic. So here's a simple picture of that in action. So let's imagine the target was just a torus, first manifold that came into my head. And I've drawn here the image of the initial data at U0. So of course, the energy is giving you some rough idea of how stretched this is. So as you do a gradient flow, then that curve is trying to reduce its energy, essentially trying to shrink. So a little bit later on, it might look something like that, going around the torus. And then eventually, as time converges to infinity, then you'll converge to your harmonic map, your geodesic. Okay, so that poses an immediate question, which is, well, you've said you have convergence at the sequence of times ti going to infinity, but do you actually have convergence as t goes to infinity? Okay, so in the picture here, it looks like maybe you should do, right? And actually, there's a parallel story that's just popped into my head of when Eel Sampson introduced the harmonic map flow. So they actually proved a convergence result, first of all, at a sequence of times Ti going to infinity. And then Hartman came along very shortly afterwards and showed that you do actually get, in their situation, where you're mapping into a certain type of target manifold, a negatively curved target manifold, you do actually get nice convergence as T goes to infinity. Okay, so however, in general, the answer is no. So you can't just switch from the convergence at a time sequence Ti going to infinity to T goes to infinity. So from the picture above, if you've never seen anything like this before, that may be a little bit weird, but actually the idea is extremely simple. So let me sketch the idea in just in finite dimensions. So what I'm doing here is drawing a picture. This picture here is a graph of a function f, and it looks like a sort of mountain, if you like. And then what are these blue lines? Or this blue line, in fact, is a blue line which spirals down the mountain. Well, think of it like a, it's a bit like a helter-skelter, if you like. So I've zoomed in a little bit on the left here, and you can see I've sort of chopped out a little path or a little gully that goes round and round and round. So of course, if I start my gradient flow at a point x0, where the function is within one of these gully, or in the gully, then the gradient flow will just take you round and round and round. And I've designed this function so actually the gully is infinitely long. It just keeps spiraling around, it gets flatter and flatter, and just spirals around and around forever. Okay, so if I do this gradient flow, so that would be the usual gradient flow, I'm just in 2 dimensions, then we're going to get this whole circle of limit points here. Okay. So what about infinite dimensions? So how are we going to extend this to the harmonic map flow? So I'll always write HMF for harmonic map flow. In other words, the situation we had before. Well, it's actually very simple. So the trick is just to pick the right target. Okay, so this is an example from the mid-90s, but there were earlier examples of, in the context of, say, minimal surfaces and harmonic maps. So we're going to take the target N to be a product of R2 and S1, but I'm going to not just take the Cartesian product, I'm going to take a warped product. So what does that mean? Of course, that means that I've got a function f from R2 to, well, positive function. And as I go around R2, then I'm going to scale my S1 by, I'm going to scale the standard metric on S1 by this function f, okay? So don't worry that this isn't compact, this target. You'll see the idea, it works anyway, although normally my target has to be compact. Okay, so so what sort of initial data am I going to take? So U0 is my initial data, and it's going to be the identity from the S1 to the S1. So theta goes to theta. And it's going to map the whole of this S1 to 1 point x0 in the R2. Okay, so if you work out the energy of this map here, then it's basically going to be the energy of the identity S1 to S1 times f at whichever point you're considering here. So if you do gradient flow, if you do harmonic map flow, you just actually end up with a solution like this, which is exactly the same form. Theta always goes to 1 point independent of theta, but that point now depends on time. And of course, that x here is just going to do gradient flow for your f. So if you choose your f like you did before, then we're going to get the same sort of winding behavior. Okay, so that's all very straightforward. So this problem of non-uniqueness, there's a sort of general meta theorem, which is that if everything inside is real analytic, then nothing bad should happen. So that's because of something called a Lawyer-Sawicz estimate. Originally, Loyer-Seiwich did it in finite dimensions, and then it was extended to infinite dimensions and to really be useful in geometric analysis by Leon Simon. So now, by the way, I can work on a domain of any dimension and do harmonic map flow there. So here's the basic idea. So let's say we're in a situation like we had before, where, where we have a sequence ti going to infinity, and we have convergence at that sequence. Okay, so the real analyticity of n essentially gives you one very special estimate. This is the so-called Loyer-Seiwich Simon estimate, and let's try and deconstruct what that's actually saying. So it's saying, if you take your u infinity, which remember is the limit that we're considering here, then this u infinity has a small neighborhood, so that if v is in the small neighborhood, then the energy of v minus the energy of this limit is controlled in size by this tension. So remember the tension, this is the gradient of the energy. Okay, so it's controlled in the sense that we do have an exponent theta here, and this theta is between half and 1. So the case half would be the strongest situation. In fact, normally to get a half, you would even need to put in a constant c in the estimate, but let's not worry about that. Okay, so the other ingredient, which is just definition of gradient flow, is that if you take the derivative of the energy, or equivalent the energy minus the limiting energy, then you get, just by virtue of it being a gradient flow, you get minus the L2 norm of the tension squared. Okay, so what do we actually want to achieve here? So what we're trying to show is that U has a decent limit as time goes to infinity. So what we want to do is control how far U can move in, let's say, L2. Once you control it in L2, then some interpolation will control it in other norms too. So if you want to control how far U moves in L2, then we better control du by dt in L2. Okay, so du by dt is just this tension. So what we really need to control, let me just scribble it in the corner here, what we really need to control is the integral all the way to infinity of the tension of u of t measured in L2. So if you can control that, then if you go far enough along in time, then you've got a smaller and a smaller distance that you can go from there on. So in particular, you can't infinitely wind round and round and round like we had before. Okay, so we're trying to get an estimate for this integral. And if you look at the this last line here, we've almost got it. So if you look at this estimate here, if we didn't have this 2 here, then we could just integrate this equality, and we'd find out that this integral we're trying to control would just be the difference of this at time t and this at time infinity, which is 0. So we'd be done. Okay. Unfortunately, there's a 2 here, so that doesn't work. It can't work because the example that I gave you before shows that it can't work. Okay, so that's where this estimate here comes in, which seems to almost work the other way because the tension is being controlled from below and we're trying to get an estimate from above. But of course, as many of you know, these combine quickly to give what you want. So the easiest way to see that is to differentiate the quantity we had before, but now with a power, 1 minus theta. Remember, theta is between half and 1. So just differentiate that out using just normal calculus. This first part here is 1 over this here. So we can turn that into a 1 over that. And that's where this came from. This part here is just this. So we can turn it into a integral tension squared. So of course you get cancellation there and you end up with this. So we've controlled the tension in L2. So now we really do have an estimate here that we can integrate in time and get control on this, okay? And you can, yeah, so there is the estimate. I've actually written it out. And you can even use the same ingredients a little bit more carefully to say how fast the energy decays, and so how fast you reach your limit. Let's not worry about that. Okay. So let's say let's say we don't have smooth convergence UTI to U infinity. So the theory above, this Loisewicz-Simon theory, really relies on the fact that you have reasonably strong convergence to begin with at a sequence of times Ti. So let's just go tangentially for a second to think what happens if we don't have the smooth convergence. So the sort of most famous situation where that occurs is when you're in dimension 2, and then there's a nice theory of a harmonic map flow that was started by Michael Struve, where you get maybe bubbling occurring. Okay, so if you get bubbling occurring, then basically this old theory fails, and you have to do something else. So I just want to talk about that a little bit because it's actually a source of a lot of really interesting open problems. So let me give you the I think probably the first theorem of this form, actually my PhD thesis, very long time ago now. So this situation is where you have harmonic map flow, and the domain, which we've already decided is a surface, let's say it's S2. And let's say it maps into another surface, and then the interesting case is when that surface is S2. So we're doing harmonic map flow from S2 to S2. So the theorem, which I won't explain in detail, basically says if all the bubble maps, if you know what that is, and if this limiting map, which I think actually in that paper, the phrase body map was coined. So if all of those have the same orientation, then actually everything works. So you get nice uniform convergence UT to U infinity as T goes to infinity, let's say in L2, but better convergence away from the bubbles. And also any, so I apologize, by the way, if you don't know what bubbling is, I will not be using it for more than another 2 minutes. But for those of you that do, then bubbling involves energy concentrating near a finite number of points. And in theory, you could have that energy that's concentrated drifting around in the domain, maybe slowly. So in this theorem, you also find that that doesn't happen. So here's an interesting conjecture, which I think is still wide open. So if you have the harmonic map flow into a real analytic target, then you should have what you might call uniform convergence, in the sense you have convergence as T goes to infinity rather than Ti goes to infinity. And probably you shouldn't have concentrated energy drifting around. Okay, so it's very easy to make that conjecture because of what we know in the nice smooth case, but actually the techniques in the smooth case just don't work. Okay, if N isn't real analytic, then all hell can break loose. So actually one question that you can ask immediately is, let's say you do a bubbling analysis, for those of you who know what bubbling is, at infinite times. So you'll take a sequence of times Ti going to infinity, and you'll have certain points where energy is concentrating, maybe at a different sequence of times, then the energy is concentrated at a different set of points, sort of what I was talking about before. It's actually much worse thing can probably happen. So there's a non-rigorous example from a long time ago, which is that actually you can have a sequence of times going to infinity where you have bubbling, and another interwoven sequence where you actually don't have any bubbling. Okay, so energy can sort of concentrate and then deconcentrate and then concentrate and deconcentrate. So very crazy things. There's also the question, I think this is almost the last thing I'll say about bubbling. There's also the question of bubbling at finite time. So singularities can occur at finite time in the harmonic map flow. And there's a well-known way that was initiated by Struve following Sachs-Uhlenbeck in some sense to extract bubbles from singularities. So you do some rescaling. And then there's a question of whether you could, whether you have any non-uniqueness now. So you don't have non-uniqueness of the form of concentrated energy moving very rapidly around. That can't happen ever. But what you can have is that choosing two different sequence of times ti going up to t gives you a completely different set of bubbles. So basically the image of the bubble is going round and round and round and round, and then just goes to infinite speed as you approach this finite time. So if you capture the bubble there and there, you'll get one set of bubbles, and if you capture it there and there, you'll get another set. Okay, so that really can happen. Okay. So let me switch to a different gradient flow that I want to talk about for the rest of today. So this is, we sometimes call it the Teichmüller harmonic map flow. So this is a flow that I introduced with M.Rupflin some years ago now, and it's a flow of maps from a surface. If the surface is S2, then it's just the harmonic map flow. But for other surfaces, it's something different. So if the surface is a 2 torus, then it actually ends up coinciding with a flow that was introduced by Ding, Li, and Liu. But, and actually that's, for this talk, it's actually the case of most interest to us. The case of most interest for the flow itself, where lots of weird exotic things happen, is the case of higher genus, and then everything is more complicated. So what is this flow? So we're going to do a gradient flow for the energy, but instead of doing a gradient flow for the energy just seen as acting on maps U, we're going to see it as acting on pair, map, and domain metric G. So think of little g as the metric on M. Okay, so we have, let me just remind you, we got the setup then that U is basically mapping from M, G to our target manifold, which could be of any dimension, by the way. Okay, so what we're going to do is constrain the G, the domain metric G, and I'm going to constrain it to lie within this space of metrics M sub C, and that's the metrics of constant curvature. So my domain surface is always going to be closed. In fact, just take it to be oriented. So I'm going to take the metrics to be not only of constant curvature, but by scaling, we may as well take them to be the constant to be either -1, 0, or 1, depending on the genus, as usual. There is a bit of flexibility if we're on a torus, because then you can just scale at will. So let's normalize in that case. So that's the C equals 0 case. Let's normalize so the area is, say, 1. Okay, so we've got a variational problem here. So what do we know about critical points? Well, if you've got a critical point, then it's a critical point as U varies. So certainly U is harmonic. But of course, it's then also a critical point as G varies. And if you work out what that means, it means that G is a metric which makes U conformal.
Peter,
okay?
There is a question in the chat. I think.
Oh, okay. I should open the chat.
I can read it if you want. So it's why not allow the codomain metric to vary?
Oh, well, you could do that in certain situations. It depends what you're actually trying to achieve. So I'm a little bit suppressing in this talk what we were trying to achieve with this. It's hidden a little bit on the next line, which is, well, let me just give you the next line and then I'll answer the question. So I've just said that U is harmonic and G makes U conformal. So this map here is harmonic and conformal. It might be constant, or it might have some points of 0 energy density, but that basically makes it into a minimal immersion, maybe some branching. Okay, so basically, by considering this variational problem, you can find minimal immersion. So I'm thinking at the outset of a fixed manifold N and imagining how I can find a minimal immersion within. So that's why I'm not thinking specifically about varying the target metric itself, but you could do that from an analysis point of view, it could be interesting. Okay, so so we want to do a gradient flow for this. So this is going to involve U and G. And we make another little simplification, which is probably best explained by just saying that we're going to move G horizontally. Okay, so what does that actually mean? So it means that we're going to move G, so of course we stay constant curvature, but we're going to ignore the infinite dimensional space of variations that I could move in, which are not really changing the metric. They're just pulling back by a diffeomorphism, which is an infinitesimal variation of the identity. Okay, so I just ignore those. So that's easy to impose. And probably the most concrete way of explaining that is that I'm going to constrain that dg by dt is divergence free and trace free. Okay. Okay, so let me quickly give you the equations, although they're not terribly important for this particular talk. So if you look at the first equation, then this is the ordinary harmonic map flow that I wrote on the first slide. Okay, but then G is also changing, and that's evolving under an equation which is a little bit harder to explain. So this is not a parabolic equation for G here. It's a little bit more like an ODE, although that can be extremely misleading. Maybe I'll say a bit more about that later. So I've written it as follows. So dg by dt moves in the direction of, well, I really want to do a gradient flow. So I want to move it in sort of this direction, which is the direction which would reduce the energy as quickly as possible. But if I did that, then I'd maybe lose my constant curvature property and I wouldn't be horizontal. So I have to do a projection onto these horizontal directions that I was just describing. This gradient maybe is nice to see from a PD point of view what that actually looks like, and that's also very easy to explain, particularly if you know what the Hopf differential is. Actually, it means different things to different people, but for a harmonic map person, then the Hopf differential is essentially giving you, if you take the real part of that, which is a quadratic differential, then you would get this gradient. So you don't need to know anything about the Hopf differential or quadratic differentials from now on, because I'm going to write it out just concretely. If you choose nice coordinates and then you just rotate the coordinates so that u sub x and u sub y are orthogonal, then there's a nice expression here. Okay, so if you're not conformal, so u sub x squared is not the same as u sub y squared, then it will stretch your x and shrink your y to try and make it conformal. So everything works as you'd hope. Okay. So let me give you a precise result. This is one of the easiest results that we proved on this flow right at the beginning, but the most pertinent for the theorem that I'm going to tell you in a second. So this is a result with Malny. So what does it say? It says, let's suppose you have a solution to this gradient flow and that it exists for all time, and also that the metric G does not degenerate. And the easiest way to describe what I mean by does not degenerate is I've written in a box here. So what is this L here? So this L is the length of the shortest closed geodesic. So what can happen, particularly in higher genus, is that the surface can degenerate where it sort of looks like this. But and this geodesic gets very small, but we don't have to worry about that now. Let's just accept that we're in this nice situation. So what I really want to say is there exists a sequence of times so the flow converges to a critical point. So the critical point would be U bar, comma G bar, but I can't quite say that in this theorem. So what we actually proved was that at a sequence of times Ti, you get convergence to a nice limit, but only if you modify by a sequence of diffeomorphisms. Okay, so we've got a sequence of times, we've got a sequence of diffeomorphisms, I'm calling them Fi. And then we've got 3 and 4 giving you the actual limit, so a constant curvature metric G bar and a harmonic map U bar. Okay, so I get convergence as long as I pull back by my diffeomorphism. So that's written here in A and B. So if I pull back the metric, I get this limit. And if I pull back the function, in other words, I compose the function with the diffeomorphism, then I get this limit. Let's just say for simplicity in L2, although the convergence will be a lot better in practice. Okay, so after parameterization by these diffeomorphisms, you get a minimal immersion. Okay, so that immediately begs the question, which was asked by everyone that I ever gave this talk to back when we proved it, which is of non-uniqueness. So do you actually need these diffeomorphisms Fi? Or maybe you just have GTI converging to G bar and you have UTI converging to U bar. Okay, so that's a sort of different non-uniqueness question to the usual ones that I was mentioning. By the way, there are many other non-uniqueness questions. The original ones were to do with blowing up singularities of harmonic maps and minimal surfaces. I won't talk about today. Okay, so here's the non-uniqueness question. Do you need the diffeomorphisms Fi? Let's say you don't need the diffeomorphisms Fi. Then does the flow converge as t goes to infinity, or do you really need that sequence ti going to infinity? Okay, so let me give you a theorem. I should say, sometimes when you have a question like this, you pretty much know what the answer is. You just don't quite know how to prove it. When we proved the theorem on the previous slide, we really had no idea. Anyway, now we do. So this is a theorem that's being published this year. And basically, you really do need the diffeomorphisms Fi. So there exists a solution in this very simple theorem from 2 slides ago, which is actually not so hard to prove. I won't go into it maybe for reasons of time. So that you do need the diffeomorphisms. There's no way of getting it without. So maybe the cleanest way of saying that for people who know what it is to say that these Fi diverge in the mapping class group. Don't worry if you're not familiar with that. Okay, so also you could choose different sequences, Ti going to infinity, and get completely different limits. So you get 2 different minimal immersions that were completely disjoint. So you can have the most extreme form of non-uniqueness, although with the caveat that everything I'm doing at the moment is in the situation where you don't have any bubbling. Actually, I should have stated that in the theorem up here. When I say do not degenerate, I mean this box thing here. Oh, actually, no, that's true even if there's bubbling. I remember now. That's why I actually stated this as an L2 convergence. But I'm principally interested in the situation with no bubbling. Okay. So let me talk you through a little bit the ideas in the proof in the last 15 minutes. So I'm going to prove, as I mentioned before, this theorem in the situation that the domain is the torus. And as I mentioned before, that's a situation where you can show that our flow is equivalent to a flow of Ding, Li, and Liu that you can read about from about 2006, maybe, in their Inventiones paper. Okay, so why is the torus particularly nice, particularly simple? Well, it's because the metric G, the domain metric G, will move within a finite dimensional space. So it really is just evolving under an ODE. So let me talk about the general situation for a second. So in our flow, the way it's set up, the reason why we took these, the reason why we took G to vary in a horizontal direction is because the space of horizontal directions is actually finite dimensional. So at each G, there's a plane, it's actually a finite dimensional subspace of horizontal directions. Unfortunately, that distribution of planes is not integrable. So when you start moving around, then you might come back to the same metric, but modified by a diffeomorphism. But that complication, it really is a very beautiful complication, actually. The geometry is very nice behind it. It doesn't happen in this torus case. So we're just going to construct the example in this situation. So this space here I'm talking about, M star, I'm going to describe on the next slide. So this is the space that the flow will move G within. So what is this space? So let's let me walk you through the slide, because I'm not going to take it in order. So I've said on the previous slide that M is the square torus, and I've drawn the picture of the square torus actually in the middle. So look at this bit first. So this is the standard picture of R2, and I've got the unit square torus and done the usual identification of top and bottom and left and right. Okay, so of course I want to consider other conformal types, and the picture to have in mind is maybe this picture here. So if you imagine that parallelogram, and again identifying points on the bottom with the sort of corresponding point on the top, the usual picture. So we want to consider those metrics as well. This particular picture, which is the way you normally write it, with this sort of module A comma B, is not so ideal for us because this parallelogram doesn't have unit area. So let's go over here and just scale that picture down. So now this is unit area, okay? But it's basically the same picture on the right and on the left. Okay, so I really want to consider this torus here, but one of the things about this flow is because we're doing PD theory, you have to work on a fixed base manifold. So the fixed base manifold we're going to work on is this one. So how do I consider this metric here? Well, in the obvious way, I take the linear map TAB, the obvious linear map, which maps this to this, okay? So clearly I'm going to map this point here to this point here, and I'm going to map this point here to this point here. Okay, so now you can actually read the definition of M star. So it's all the metrics, I'll write them G, A, comma B, which basically correspond to this essentially. So they're the pullbacks of the Euclidean metric. And A and B is varying over the upper half plane. And you should think of that as a hyperbolic space, because actually there's a very natural metric, the Weil-Petersen metric on this space, which coincides up to a constant with the hyperbolic metric. Okay, so let me speed up a little bit. So what we're actually going to prove is that you can virtually prescribe the solution GT. So that's the sort of domain metric part of the solution. So a little bit more precisely, if you give me a family of metrics on the torus, I think that M star used to be a star, should be up here. Anyway, so this is a family of metrics parameterized by a real number S. Okay, so with a few little constraints, if you get given that family, then you can cook up a target N, which is a bit somehow undulating, and flow within that, so that the flow, at least the metric part of it, follows very much your semi-arbitrary chosen family of metrics. Okay, what you can't really say is how fast it goes along this family. Okay, so let's do a simple example. So let's take the metrics corresponding to these parallelograms that are gradually tilting more and more and more. So G0, G1, G3. Okay, so this would be little G3, 1.
Peter,
Okay.
I have a question.
Okay.
Would you describe this deformation family as incompressible Teichmüller flow?
So the terminology there is a little bit ambiguous. So Teichmüller flow in this talk means something different. So Teichmüller flow can mean other things in Teichmüller theory, but yeah. I would encourage you just to think completely concretely, because the picture is simply this. I'm just taking this metric, this metric, this metric, and it's just diverging in Teichmüller space. Now, all these metrics here are actually the same metric in the sense that just by definition, I mean, I've written it on the bottom line, but maybe just listen to the words instead. So just by definition, you can find a diffeomorphism which isn't homotopic to the identity, which maybe twists the torus so that it pulls this back to this and pulls this back to this. So basically, if you look at the sort of integer points, G1, G2, G3, you'll actually essentially modulo diffeomorphisms have the same metric, so obviously converge. Okay, so the theorem with James and Marley, for that sequence of torus metrics, capital G sub S, you can cook up a target and a flow so that, maybe look at this bit next. So your solution G of T follows very much this flow that you've prescribed of metrics on the torus, but it does it parameterized in a funny way. So this parameterization is going to infinity as time goes to infinity, and not before. We just don't know how fast, but who cares? The point is that the distance between the actual solution G of T and the prescribed thing, as long as you go at the right speed, is actually going to 0. So this distance here is the Weil-Petersen distance, and it's essentially the hyperbolic distance if you think of in terms of the A's and the B's from a couple of slides ago. So you're basically pulling on a leash somehow your flow off to infinity in Teichmüller space. So in particular, the G of T can only converge when you're modified by diffeomorphisms. And you have this other type of non-uniqueness. Let me suppress that a little bit. If you choose different sequences of times going to infinity, then you'll get different minimal surfaces. Okay, so in the last 5 minutes, I just want to give you some idea of the proof. So I actually have maybe 3 or 4 slides, so let me select. Let me go back to basically the picture I had right at the beginning, but just in a slightly different situation where I replace S1 by T2. So in other words, by S1 cross S1. So imagine the situation where I'm T2 to R cross T2, and I've got a warping function f, which is now only living on R for simplicity, and I've just drawn this function. The important point is that it converges down to 1 as sigma goes to infinity. So just as you had before, if you take one of these very special maps where the whole torus gets mapped to 1 point in the R component, then the energy of this map is just for the same reasons as before, just given by this warping function f. So just as before, if you do the harmonic map flow, then you do gradient flow. Okay, nothing new there, but it's useful to set up the notation. And in particular, think about this metric that I've now written, this warping metric explicitly. So d sigma squared plus f of sigma g0, because that's g0 I'm going to change now. I'm going to replace it by g sigma. Sorry that my sigmas look very much like zeros, but they're just about distinguishable. So now I've got a metric on the target, which is still warped by my function f, but it's not one fixed metric I'm warping. It's changing as I go through sigma. I'm still considering the same sort of maps. So now the energy is a bit more complicated. So now it's still warped by f, but it's multiplied by the energy, which before was 1, but is now more complicated. So I'm essentially mapping from, I've got this G, which I'm assuming is in M star. So I'm essentially mapping from that G to this G sigma, which is coming from here. Okay, so it's an interesting fact that the energy of the identity from T2 to T2 between two of these, considering two different metrics in M star, has a very nice expression. And it's just a cosh of this Weil-Petersen metric, which again is just a hyperbolic distance. So that's all very straightforward, all very clean. Okay, so so what happens as you flow here so basically this warping function here is trying to increase sigma, okay? Because energy wants to reduce. But because sigma is now increasing, that's changing my G sub sigma. But then this G has to follow along very closely behind, because if it didn't, then this distance would grow, and that would make this energy grow. But we're doing gradient flow, so the energy can't grow. Okay? So then there's a little lemma that we proved. Basically, as you flow, your harmonic map flow is of this special form that's clear, but it goes to infinity, everything nice happens. So the energy decreases to 1, which is sort of at infinity, and your flow is being pulled along on a shorter and shorter leash as you go through time. Then there's a little argument to make everything compact. So at the moment I've not got a compact target. Maybe if I just say 30 seconds about that and then give you one final slide. So let me just point the following thing out. So if you were just looking at a Cartesian product and the most, the Cartesian product metric, then I could compactify this, doing this stupid thing by winding R around a circle. So identify sigma comma p with sigma plus 1 comma p. Okay, in our game we have to do something a little bit more clever, which maybe I'll suppress some of the details for time. So I'm going to identify sigma comma p with sigma plus 1 as before, but phi of p. So basically, because my metric's changed, it's changed to something which is the same modulo diffeomorphism. So you have to then modify by that diffeomorphism, which I've written here as phi. So let's not dwell now on what that phi is. Okay, so that still is not quite the full answer, because that metric here doesn't have the warping function. But basically there's a way that instead of winding round a circle, you can wind round a cylinder, and each time you move a little bit sideways, and that allows your F to drop more and more and more. Then you limit to some sort of limit on the cylinder. Okay, so in the last slide, let me actually give you a positive theorem. So this is one slide I managed to reuse from an earlier talk. Everything suddenly looks very clean. No scrawly handwriting. So this is a positive theorem in the same paper with James and Malney. And as usual, you use this special hypothesis that n is real analytic. Okay, so let's suppose we have a smooth solution where we do a bubbling analysis. We get times j going to infinity, so that if you like, the gradient of the energy at these times goes to 0. That's always what you do when you do a bubbling analysis. And let's make an additional assumption that we can do that so that you don't have bubbling. So that's maybe the cleanest way of writing it. And let's make this assumption that you don't have this degeneration of the domain metric. So this is quite easy to arrange in many, many situations that I don't have time to go into. So then the theorem says you don't need a sequence of times ti. So you really can, and you don't need the diffeomorphisms anymore. So the diffeomorphisms are really coming from the non-real analyticity. Now you just get straightforward convergence, the best you could hope for, as t goes to infinity, not at some sequence of times. And what we have in mind there is that we're going to use this theorem, or someone will use this theorem sometime, hopefully, to take whole families of maps and deform them together to families of critical points, which is a sort of common thing that you do in topology. Okay, my time's up, so I'll stop there.
Thank you very much.